So finally, ito na yung last video natin for the SEM. And for this video, I will be giving a walkthrough for the greedy algorithm for the traveling salesman problem. So this video is an aid for those of you na hindi pa nakakagawa ng machine exercise for the Module 9. So, the overview of this presentation is number 1. I'll start with the greedy algorithm for the traveling salesman problem. And then, since this is our last video for the SEM, I will give some notes on algorithm design. And that includes the problem complexity and some limitations of computation. And then, why is it okay to settle down for good enough solutions. So, let's start with the greedy algorithm for the traveling salesman problem. In the description of the machine exercise, I actually provided this link to give you a guide how to solve this problem. And I used the same problem na sunod natin nung ME7 because I needed you to be familiar with the problem and the optimal solution. So, this problem is known to be a hard problem and so far, walang mabilis na algorithm for this problem. When I say mabilis, the running time of the algorithm is polynomial time and it's guaranteed to be optimal. So, most of the time, greedy algorithms are used to provide approximate solutions. So, when we say approximate solutions, these are solutions with guaranteed quality. So, it's not always guaranteed to provide the optimal answer, but guaranteed siya with respect to some constant factor, gaano siya kalayo from the optimal solution. So, again, when we solve a problem, it starts with modeling the problem. You have a real-world scenario, just like what we have in our ME7. And then, what we can do as computer scientists is to model it combinatorially. So, we can model it like graph problem and the problem as the traveling salesman problem if you wanted to minimize the tour. So suppose this is our graph representation of the problem. And take note that this greedy solution only works for those problems that are obtained from metric spaces. So when I say metric spaces, the edges that connects one node to another node. So formally, the triangle inequality is the size of this is less than or equal to the sum of the sides here. So, if you noticed, if naglalakad kayo sa UP before, when you go to a certain corner, sometimes yung makikita kang hypotenuse doon. It's because the hypotenuse dun sa corners na yun is mas mabilis compared if you go through the sidewalk. Yung Euclidean distance obeys the triangle inequality. So, it's a metric space. Everything that is obtained from the 3D space ay metric. Pero it's not true for if this edge weights are time going from one place to another. So sometimes mas traffic dun sa area na to compared kapag ka nag-longer route ka. So hindi na siya necessarily metric. Ano pa? Aside from the time, sometimes the fare. For example, if you go from one place to another place, yung flight, the direct flight is mas malaki compared if ang flight mo ay may layover pa to some airport. So, hindi lahat ng mga model of real world scenario is metric. So, in this case, since we are using the Euclidean distance between places and location, we are guaranteed that this is a metric case. So for this approximate solution, we have this algorithm. Okay, so for this algorithm, since we are already familiar with the minimum spanning tree, the first step is to build the minimum spanning tree given the graph G. So the minimum spanning tree from our previous videos is a spanning tree with a minimum total weight. So getting this minimum spanning tree is via Prim's or Kruskal's algorithm. But just to illustrate, let's use Kruskal's algorithm. So the first part of the Kruskal's algorithm is the arrangement of the edges with respect to weight. So 6, 7, 7, 8, 9, and 12. And then let's start with the least edge. And then we will add the edge if it's it if it's a legitimate tree, pero we will not add an edge if it will introduce parang a cycle in the graph or in the resulting MST. So again, since this is a greedy algorithm, we produce the solution piece by piece. So it starts with this two vertices na connected na via 6. So this part. And then we have 7 and 7. So arbitrarily, we can choose between the two. 7, okay, 4 and 3. We will add this in our MST. And then another 7 here. So hindi pa siya nag-perform ng cycle. However, if we add other edges in this graph na wala pa dito, it will produce a cycle. So for example, in this case, for 8, this one, if we add 1 to 2, then it's already a cycle. If we add 1 to 4, it will introduce cycle. And same goes with 4 to 2, it will produce a cycle. Okay, so if we have the MST for the graph, this is the basis for our second step, which is the DFS traversal. Since this resulting tree is an unordered tree, initially wala talaga tayong root node for this structure. And generally, it's just a tree na walang ordering yung mga branches niya. So, if we have a constraint na ito ang laging starting point, then what we can do is to hang the tree with respect to that specific node. So imagine that you can, let's say, hang this tree 2 as the root node. Tapos you have a single child 3 and then merong left and right. So as a convention, para pare-pareho tayo ng sagot for the ME9 is that try as much as possible to arrange the subtrees according to the weight. So, lesser weight tapos heavier weight yung nasa right side. Okay? So, if we can have an ordered tree, so it's already rooted or oriented tree, rooted na siya, and then you have certain arrangement of the siblings. You can have something like this. Okay? And so, if we set 1 as the source, we have this orientation of the obtained minimum spanning tree. And then what we can do is to follow step 2. For step 2, we will traverse this tree in depth first search. And then the depth first search is in pre-order manner of enumerating the vertices. So just to visualize, this is our graph, and if we have a pre-order walk using DFS, we have 1, 3, 2, and 4. And as a convention that we mentioned in our ME9, to rearrange the children according to increasing edge weights. So we have this DFS traversal of the oriented tree. So we have 1, 3, 2, and then 4, and then back to 1. Since we already have a traversal, we can of course compute the cost given the original graph. So here's the original graph. Given the tour that we obtained from the previous slide, we have 1, 3, then 2, then 4, and then back to 1. So if we will use this and use this original graph, we have 7 plus 6 plus 12 plus 9. So we have 7 plus 6 plus 12 plus 9. So that's 34. But if we use the exhaustive algorithm, the optimal solution should be 30. So even though we don't get the optimal solution, the algorithm provided is known to be a 2 approximation algorithm. So at the worst case, regardless of the size of the graph, if we have an optimal solution of 30, then this algorithm has a worst cost of 60. So, hindi na siya lalagpas ng 60. Hindi tayo pwede magkaroon ng cost na 70 or more. That is regardless of the size of the graph. Okay, so we are now on our second part of this video where I will give some few notes or parting words since we are already ending the sem. So generally, there is no recipe for solving a problem. And if we are given a real world problem, the first thing that computer scientists needs to do is to understand the real world scenario first. And then look at our um, existing models like trees and graphs to represent the scenario. If we can represent those real world scenario to something like a well-known graph problem like TSP, knapsack problem, and so on, then it's just a matter of translating the actual input to input that are readable in a computer. So that's the first thing, understanding the problem. And then the second step is understanding the scenario. So number one, do we have the computing capability or the device to solve that problem? Do we have a high performance computer? Do we have a single machine? And then that could be your limitation in deciding whether we can opt to optimize on the memory, optimize on the running time, and so on. And then aside from the definition of the problem, we also need to identify the complexity of the problem. Is it an easy problem? Is it a hard problem? And to know whether it's an easy problem or a hard problem, marami ng scientists ang nag-identify ng hardness ng mga problem. And in fact, there is an area called computational complexity that tries to classify all this problem, just like parang zoo, parang may taxonomy of different problems, and classified sila with respect to gaano sila kahirap isolve. So if it's an easy problem, then you can always opt to provide an exact solution for it. So laging optimal yung solution kasi mabilis lang naman mag-run. However, if it's a well-known hard problem, then you can go to solutions for hard problems. And one solution is providing an approximate solution for the problem. Since we are now on the next thing is we wanted to know what algorithm design technique to use. And as mentioned in our previous sessions, there is a particular property of a problem. And yung specific property na yun yung reason why the algorithm design works for it. So, for example, for problems with a dynamic programming approach, kailangan may overlapping problems siya and may optimal substructure property so that we can create a recursive relation for it, and then we can create a dynamic programming for it. And most of the time, and all the time, the dynamic programming approach provides the optimal solution. However, matagal mag-run ng mga dynamic programming algorithms. Hindi lang siya as simple as the creating the table, but most of the time, since it's a recursive formula, parang via memoization, i-check mo na lang siya every time we have a computed solution for that sub-problem. And on the other hand, we have the greedy algorithm for problems that are easier to solve. And for easier to solve problems, greedy algorithm works. Pero for hard-to-solve problems, the greedy algorithm provides only the approximate solution. And there is a categorization of problems that are easy to solve using greedy. At ito yung mga problems na may optimal substructure, pero not necessarily may overlapping subproblems. And if you wanted to know more about these problems, then look for properties like matroid properties. These are the problems with an optimal greedy solution. Okay, third step is designing an algorithm based from understanding the problem and understanding the scenario in steps 1 and 2. So, given an algorithm, hindi naman siya ideally very, very exact na pseudocode or code type. Pwedeng it's just a general idea. And medyo loose yung definition. And it's up to us to identify a particular data structure that we can use for the implementation. And the algorithm's running time is very dependent on the data structure that we use. So remember in our greedy algorithm for the Kruskal's and prims. So for the prims algorithm with adjacency matrix, iba yung running time niya, n squared. Pero for the priority queue implementation, we have m log n. Okay, so yeah, so malaki yung impact ng data structures. So sometimes researchers creating algorithms for a problem sometimes improve dun sa data structure lang, and then they can have an running time of the algorithm. The next step will be proving that the algorithm is correct. So, for different types of algorithms, iba yung tinatry nating i-prove. Yung correctness dito could mean different things. So, for exact algorithms, you need to show that this algorithm always produce the optimal solution. Pero for approximate solutions that can have a guaranteed quality, what you can do is to prove na hanggang ganun lang yung quality niya. At hindi siya mas magiging worse than that. If you have a randomized algorithm, for example, what you can do is to prove that the algorithm has an expected quality na ganito. So, it depends on the type of algorithm. Pero, sa mga napag-aralan natin before, usually, we're dealing with the exact algorithms naman. So, you just need to show that correct and optimal yung sagot. Optimal if it's an optimization problem. And then, next is to analyze the algorithm. Most of the time, we analyze the algorithm with respect to the running time. But we also need to inspect the memory usage of that algorithm, especially for devices with limited capacity, memory capacity, like mga IoT devices na may maliit lang na onboard memory, and then tinatry lang nilang isend over to some database server. So, it's a case-to-case basis. Depende sa kung ano yung resource na scarce, yun yung tinatry nating i-minimize. But in general, you can analyze the algorithm with respect to resources na ginagamit niya. And resources here can be the running time, can be the memory, can be the information na nire-read niya. It could be communication if it's multiple devices na nasusolve ng problem. So, marami pang other metrics to measure how your algorithm utilizes resources, and that's part of the analysis. And then lastly, if you're sure that the algorithm is correct, and after some analysis, you can say na okay na yung running time at pasok naman siya dun sa computing capability ng device, then it's time to code for the algorithm. So, yun yung process of algorithm design and analysis. Although there is no single recipe that solves the problem, at least may guideline tayo how to design an algorithm for a particular problem. Most of the time, we are already using algorithms from existing libraries. So, yung mga naapag-aaralan natin sa class, those are already well-known algorithms for the problem, and we can already see some existing implementations of those algorithms. So that's one. But if you wanted to create new algorithms for a particular problem, you need to make sure that that algorithm is actually an improved version of the previously known algorithm for that problem. And with respect to the algorithm design technique, minsan it's a combination of different design techniques. Hindi lang siya necessarily it's just a greedy algorithm or this is just a dynamic programming algorithm. Sometimes it's a combination of transform and conquer, and then saka mo gagamitin yung greedy algorithm inside the conquering part. Sometimes we just use a combination of multiple um, algorithms and then we combine it to solve a bigger problem. So, medyo malaki pa yung area at medyo marami pang pwedeng magawa kasi marami pang problems na hindi pa nasa-solve. Why? Because if you change the input specification, you modify the specification ng output, you add additional constraint in the input, magbabago yung problem definition. So, it needs another algorithm to solve the problem. So, I guess, yun lang. Medyo marami na pala yung mga nabanggit ko and medyo compact na siya dito sa last part. But I do hope that it inspires you to continue working on designing new algorithms at hindi lang tayo gagamit ng mga algorithms na existing na. So, ayun lang. And I hope na may natutunan kayo kahit very brief and very challenging tong SEM na to. So, see you again next SEM for other CS subjects.